We are group 4 and this is our experiment 6 torsion of bar. Uh, we are 4 members in the group: Luqman, Siafir, Hussein, Noor Anis. So this is my part introduction. Torsion rod bar or bar that device twisting and has a strongly propensity to revert to its untwisted state. Torsion bars are long spring steel components used in vehicles with one end fixed permanently to the frame and the other end rotated by a lever attached to the axle. Thus it gives the car spring movement. Abstract: The purpose of this experiment was to investigate the link between torque, the angle of a circular cross "T", and the material properties bending moment under various loads. The apparatus served as a short shaft and base frame. A short shaft in the bearing has a three-choke facing the clamp and torsion head on the outward side. A base frame has a clamp at one end and a ball bearing in a housing plumber block. At the other hand, at the other end, the torsion head was wrapped in a hanger string with an effective diameter of 75 mm. Rod length spines were held in place by the spinning chuck and fixed clamp 450 mm. On a base that can be moved along the specimen line. A scale of degrees in the shape of an arc was fixed when a weight was applied to the hanger cord. A pointer on a spring steel strip marked the rotation of the specimen. A graph of the angle of twisty with torque was being displayed once the data had been gathered. Calculating the modulus of rigidity and comparing the results to the theory based on collected data and graphs. The conclusion was drawn, however, due to several mistakes made during the analysis. Our outcome might be theory. Objective: to research the material's characteristic bending moment under various laws. Theory and related applications. Apparatus: when the bar is subjected to torsion, it can be imagined that the bar is made up of the multiple individual discs that rotate relative to one another when the torque is being applied. Therefore, the distribution of the shear spring that were created by the torsion within the circular shaft can be determined. Furthermore, this will show that shearing strain varies linearly with the distance from the center of the cross-section. The change in the angles created by both sides of the shaft can be measured to obtain shear stress, and this is the following formula.
Now I will present about the methodology of this experiment. The apparatus we use in this experiment is torsion bar testing machine, aluminum alloy rod, steel rod, nylon rod, spanner, digital clipper, ruler, and load. Step by step. The first is the diameter of aluminum alloy rod was measured by using vernier caliper. Second is the aluminum alloy rod was clamped in the fixed position. Third step is the pointer was calibrated to 0 degree and the rotation scale was set at length 40 cm from the fixed clamp. Fourth, the load hanger was hung and 5 Newton load was at the twist angle of the pointer show was recorded. Step 4 was repeated by increment 5 Newton each time until the total load on the hanger reached 40 Newton. Then, step 1 to 5 was repeated for length of rotation scale is 20 cm. Then, step 1 to 5 was repeated for length of rotation scale is 20 cm from fixed clamp. Step 1 to 6 was repeated for different material of rod, nylon and steel. In step 5, for nylon rod only, we use small range of load 1 Newton until 5 Newton because it fragile compared to other two material. That's all for me. Thank you. Okay, and I'm Shafiq. I will present about the result of the experiment. For the table 1 is data for aluminum alloy rod. The diameter is 6.31 meter, and this is the result we get after experiment. After that, we need to do a graph, which is angle of twist vs angle. The reason we need to do a graph is from the graph we can get the slope is equal to m equal to angles of slope divided by twist of angle. So the slope we get for m for 100 millimeter is 0.0101, and for 200 millimeter we get is 0.0051. To calculate the modulus of rigid G of material, the formula we get is G equal to L divided by mj. The J is 155.6386079 millimeter square. Then we proceed to find the modulus of rigidity G of aluminum alloy. For 400 millimeter we get is 40,579.54 Newton over millimeter per square. For 200 millimeter, the result we get is 40,436.61 Newton over millimeter square. So after we get the two for 400 millimeter and 200 millimeter, we need to calculate the average of G. Then we get the average of G, modulus G of aluminum alloy is 40,408.0795 Newton millimeter square. For the table 2 is data for steel rod. Diameter is 4.99 meter. And after that we need to do a graph. And from the graph the slope is for 400 millimeter is 0.0101. Then we get the modulus of rigidity G of aluminum alloy is 37,278.56 Newton divided by millimeter square. For the table T is data for nylon rod. The diameter is 6.525 meter. The result is here in the table. After that, we need to do an angle of twist vs angle. And from the graph, the slope we get for 400 millimeter is 0.00969, and for 200 millimeter we get is 0.0051. And for modulus of rigidity G of aluminum alloy, for 400 millimeter, the G is 18,664.29 Newton over millimeter square. For 200 millimeter, we get G is 20,625.85 Newton millimeter per square. And from that, we can get the average of the modulus of rigidity. We get is 50,645.07 Newton divided by millimeter square. That's all for me.
Okay, Assalamualaikum warahmatullahi wabarakatuh. So I'm Luqman Hakim. So I will present about discussion for this experiment. So the discussion for the experiment is three distinct material, which brass, steel, and aluminium were subjected to torsional test, and the value of rigidity modulus and shear stresses were computed using the experiment data. So first one, steel has the maximum value of modulus of rigidity and applied top deck pressure, which means that is the strongest material from available three material, and so it can withstand higher shear stresses than other two materials. Okay, that's for steel. And the second one is aluminium. Aluminium came second among the three materials as it can bear more shear stress and apply torque than brass, but cannot take as much torque as steel can. It can take more angular displacement other two materials and is due to material property called ductility. Okay, that is for aluminium. For brass, has third position among the available materials. Although its modulus of rigidity is greater than aluminum, but it fails at lower torque than aluminum. It has least value of angular displacement at the fracture. We show that it has lowest ductility among the three. Okay, example of calculation for the specimen's polar moment of inertia are given above in the calculation section. Human error throughout the experiment when calculating the apparatus, applying weight and obtaining readings can change the outcome. The machine limitations can also lead to reading errors. Okay, the diameter of the shaft, not the length of the shaft, determines the second polar moment of inertia J. Therefore, the length of the specimen has no bearing on the calculation of the polar moment of inertia. Okay, the scale must be stable and not oscillating when reading torque, since a fluctuating scale is challenging to read and can result in reading errors. The exact point at which torsion loading will cause failure cannot be predicted. The location where failure most frequently happens is when there is an internal flaw or crack. If not, the point where there is the greatest concentration of stress will be the point of failure. Okay, we go through with the conclusion for the experiment. So the conclusion for the experiment is the shear modulus of a material is measured using the torsion test. Is the relationship between this angle and tau. Numerous variables such as whether the load was applied too rapidly or whether the material had already been used could have influenced the outcomes of our trials. These things could have affected how we responded. However, by examining the torsion graphs and the shear modulus, this lab helped me comprehend the properties of the materials. The information we gathered from this assessment helped us understand how each material behaves. In fact, it tells us whether or not to the material would fail under a specific load. Okay, that's all for me. Thank you.